Awesome. Guys, I don't know if you guys can hear me. I just want you to raise a hand and let me know if you guys can hear me. I see that there are about 25, it's increasing. A bunch of more people are coming on LinkedIn live. Just wanted to check with you guys before we jump on to this little session. We'll keep it 25, 30 minutes and then try to do a Q&A. If you can, put your comments in the comment box and sort of respond or raise a hand. I cannot see for as of now if you folks can hear me. So if one or two of guys can just raise a hand and say, yes, the audio is great. Perfect. Awesome. So there's one person already. Kaustav, great to have you guys here. Thank you once again. Wonderful. I also see that there are subtitles as well, so it seems to be working well. There's a little banner I'm running under, but I'll just try to remove that banner. So just give you got a bit of guys a bit of an idea. So give you a bit of a perspective of Live AI. Live AI is a startup that we launched last year. It was born out of necessity, due to COVID, as you can imagine. The whole world is turned upside down. Since then, we've already done 2 cohorts that have done a wonderful job. Folks have already kind of, moved on to doing wonderful things. Some people have already created their startups. Some folks have joined some really cutting edge AI companies, and we are collaborating with some other folks who are actually bringing their enterprise sort of bosses into this ecosystem, and they're saying we need to work with Live AI. So we are partnering with some large companies in the world, firms like Atlas Copco. I'm super excited to announce that Atlas Copco is a giant Swedish giant manufacturing company with which we are going to be bringing our cutting edge Hive project to Live AI educational venture. Microsoft, we are collaborating as well in a hackathon together with a Swedish company again called Stratitech. So that is where I'll be judging the competitions. And obviously there's NVIDIA. Our relationship with NVIDIA is growing dramatically, and we are doing some really, really awesome work. So just to give you guys a bit of an update as well, I know I don't get much time to sort of give you guys an update, and you'll see me occasionally sort of sharing all kinds of interesting news and from our research front, from our enterprise projects front with Real AI, and obviously with Live AI, which is one of these initiatives. This is a free workshop. I mean, I do spend a considerable amount of time making this for you guys. So I would really appreciate if you could give me feedback. That is one. And if you're interested, because MLOps is going to be a huge topic which we would be covering. And in the coming weeks and months, we're also going to be launching a course. So maybe let me give you a bit of a perspective of why I'm doing this. Why am I giving it away for free to you guys? I shouldn't be wasting my time doing free stuff. I can sort of focus on my business. First of all, I think the MLOps ecosystem is expanding dramatically. It's creating a tremendous amount of confusion because we work with enterprises, and the first thing they ask is, how can you land your AI solution into production seamlessly? And it's very hard. It might seem like an easy question because enterprise vendors, they tend to go there and provide their solutions to customers. But I increasingly realize that it's very, very difficult, even with advanced MLOps companies that are building and stitching end-to-end a solution to the market, to get them integrated into the enterprise landscape. Why? The answer is pretty simple, because machine learning already is seen as a black box in itself when you're designing solutions and creating all kinds of, solving all kinds of complicated problems with computer vision or with natural language processing. And trying to take these models and trying to make sure that these models are efficient, are effective, and reliable, fair, and I won't get into trouble if I'm taking a vendor solution. Do I get full support and service from these vendors. And we realized this problem ourselves because we deal with enterprise customers on a daily basis. And I work closely with a lot of MLOps entrepreneurs, people who have started their companies. And we have constant conversation. For example, a company called Neptune.ai. I'm sure you're aware of it. It's a fantastic company doing wonderful work with experimentation specifically. But what we realize increasingly is that when we go back, when I put on my manager hat or enterprise vendor hat, it's very hard to convince your enterprise to just take another vendor into their ecosystem, because it really is a difficult process. You cannot just enter into a production environment with a solution, no matter how great and how fantastic and how well orchestrated. So I realized that this is important for me to share this with you. So that's why we decided that learning MLOps ourselves and implementing MLOps, and we are creating a bunch of benchmarking tools ourselves to take these into enterprise. But it's very important for us to share this information and try to see if we can get more people. So the reason why I'm doing this for free for you once again is because we want to work with talented people. So if you have engineering excellence or have worked with all kinds of complicated cloud, hybrid, and on-premise solutions with machine learning, you can always reach out to me, and we're very happy to pull you into our team. And that is one reason. The other is getting feedback from you. If you have experience in this area, and if you think there are some things we need to improve, I need to improve, I'm super excited to hear from you guys what you guys think about it. So that is the second. And the third, obviously, is that we started off. I started Deep Kafka a few years ago, 4 years ago now. It's been quite a while. Because we believe that we have to spread and expand this ecosystem beyond certain geographic regions. And that is the reason why I'm doing this for you guys. And sure enough, we want to bring all this learning into Live AI. So we're really hoping that if you're interested, obviously, you should definitely look up Live AI and see if it makes sense for you guys. And obviously, if you need PDFs, which we will be creating and all these, so you need to sign up on this registration here, but also on Live AI. You can sign up on Live AI, create your account on Live AI, and that'll help you guys be updated with all the information that we're creating. So there's a lot of stuff happening in the startups that I run. Deep Kafka is a startup, Real AI is a startup, Live AI is a startup. So they're all doing individual things in research, in productionizing AI workloads, and in teaching the world and teaching enterprises as well. So that's what we do on a regular basis. So just to give you a bit of a perspective, so it makes sense for you guys. Why am I spending my free time talking to you guys? And obviously I appreciate positive, constructive, and feedback. I really appreciate it. If there's something that we're not doing well, I would definitely want to sort of know about this. So thank you, and wonderful to have you guys here. Let me just get started. Let me go to the slide. Here we go. So design patterns. Let me just see if this is working. And I hope my face is not distracting. So I have my screen here, so I'll be looking. You'll see my face there. So obviously, we're talking about design patterns. So what is a design pattern, and why do we need to understand design patterns from a machine learning perspective? Why do we do that, and why do we need that? So I guess you guys know me. That's, let's get this out of the way. So I'm Terry. For those who don't know, I'm CEO and co-founder of a few startups. Deep Kafka is a research startup, as I just mentioned. Real AI is an enterprise startup where we build enterprise solution for our customers. And then we have Kura, which is a healthcare startup, and Live AI, which is the education startup. Awesome. So basically, the whole idea of taking MLOps and understanding from design elements or design patterns is to take your models and shipping these into production with confidence. Right. So all these large infographics, which I'm creating, for instance, this is just the picture that you're seeing on the right is just scratching the surface of MLOps, and obviously it expands across the whole paradigm of research ops, data ops, model ops, and DevOps. So this whole thing combined together is your MLOps, and all these things will come together because we're constructing all these things together. Awesome. So let's go into the design patterns. I have created a sort of a small sort of modified the definition of design patterns. So from my perspective, what basically a design pattern means is, it's a software design pattern in ML engineering specifically, where it's basically a reusable solution for commonly occurring problems that within the given context of the software design that you have software engineering in machine learning, right? So it's a foundation for robust MLOps template on how to solve problems, in different situations. And obviously, as a problem problem definition changes, the situation changes with it. And MLOps design patterns are formalized best practices. So you need to have best practices actually specifically for your MLOps in order to take these solutions to production environments authoritatively with confidence, and that's what you need. So machine learning engineering can solve these common problems when designing an application or a system. So this is the core understanding of why MLOps design patterns are needed and understood in order to formalize and templatize, if I could use that word, before taking these into production. It makes the life a lot easier for the rest of the world when you are sort of formalizing these from a design elements perspective. Understanding the design elements is super important. So first of all, there are a ton of design patterns, and I'm creating this list of about, but it's turning into a much larger sort of ecosystem, around 36 to 40 design patterns. I'll just touch a few of the design patterns just to give you guys a bit of a perspective of how they are, what they mean. I will jump into a few now, and then I will also take a few, for instance, transfer learning. So a lot of people, tend to think and everybody uses transfer learning, right? So you use transfer learning in computer vision extensively. The whole world uses it in the medical imaging or in any other of this sort of computer vision tasks, but also in language models like GPT-3. GPT-3 is a transfer learned sort of model. So you basically are training on the whole text corpus around the world, and then you're trying to apply that to your specific individual domain. So this is why design sort of elements, and I call them design elements, some folks call it design patterns. So just take a look at these. These are information I have gathered from obviously a lot of research sources that I've read, and I will provide all the references at once the slide is complete. So some of these, so let's take a look at these MLOps design patterns. Let me just try to see if I can maybe just to focus on the slide itself. Cool. So the MLOps design elements, if you just take a look at these, so the first one is embedding. So just for your understanding, embedding is a learnable data representation that maps high cardinality data essentially into a lower dimensional space. In a way that the information which is relevant to the learning task is preserved. So basically what you're doing is, well, I don't know, something happened to my camera. So basically what you're doing is you're taking these embeddings and essentially ensuring that you're preserving the learned, the high cardinality data into the lower dimension space, and the learned information is not lost. So it's all about preservation. So essentially, it's basically the heart of your machine learning today paradigm, and there are lots of different sort of variations to it. So machine learning models essentially are, they look at these patterns in the data that capture all these sort of how the properties of the model input features relate to the output label essentially. So as a result, the data representation of the input feature directly affects the quality of the final model. So what you have is you have input features, and then you have specific customer embeddings. And then you have a lot of other new forms of sort of data, the features that could be potentially added to that model. You could add audio to it, you could add video features, you could add text features, et cetera, et cetera. So those kind of things make it a little bit of a problem. But let's take a first look at understanding how this embedding looks like. So basically what happens is that, in the result, you have a data representation of the input features that directly affects the quality of the final model. And while handling data, it's structured and numeric input is fairly straightforward. So that is, pretty much easy to understand. The data that is needed to train the machine learning models comes from all kinds of categories, like I just mentioned: text, images, audio, time series, and all of the different kind of sort of, data sources. And these data representations, you need to have some meaningful numeric value to supply, your machine learning models in order to have your features essentially that can fit into a typical training paradigm. So, the embeddings provide a way to actually handle some of these disparate data types in a way that it preserves the similarity essentially between the items and actually sort of improves your model's ability to learn those essential patterns. That's what it does. For instance, one-hot encoding, you guys must be aware of, is a common way to represent the categorical input variables. For example, think of a sort of, in plurality, think in situations like gender. So today, we don't talk about genders as in male and female. There are probably 6 or 7 various sort of features you have, and probably will expand to even more, who knows. Or natality, for example, is another example. I took this example from a wonderful book one of the Google engineers has written. Natality means, child, as in, it could be, twin, it could be triplets, it could be quadruplets, those kind of things. And as the dimensions increase, you have different categories that arise from this. So, having 2, 3, 4, 5 dimensions is fine, but as the dimensions increase and as more categories come in, it becomes a problem. So the one-hot encoding high cardinality sort of categorical features like, for example, video or customer ID, et cetera, taking these as inputs into your machine learning model can lead to sparse matrix. So, which is not really well suited for your machine learning applications, specifically when you're taking these into your production environments. So that is the first problem. And the second problem of the one-hot encoding can be that, it treats the categorical variables as being very independent. And however, the data representation in case of, let's say, the natality example, you have twins, for example, in your natality data set, it should be close to the data representation for the triplets, right? And the quadruplets. And it's quite far away from the data representation of quintuplets or septuplets or octuplets. I remember there was an example of a lady who was really trying to get pregnant, and she ended up having octuplets, 8 sort of kids. I don't know how people can manage that, but again, I mean, that was something. And if you go into that, so the multiple, is most likely a twin, but it could be a triplet. So the same problem of high cardinality and the dependent data also occurs. It can happen also in images and text. So the images consist of thousands of pixels, essentially, which are not independent to one another. So a natural text sort of language is also drawn, is drawn from a vocabulary of tens of thousands, of millions of words. And a word is like walk, for example, is closer to the word run than it could be to some other word from another sort of family, right? Or sit, stand they probably are much closer. Queen, king, prince, princess, closer than the other sort of words. So that is the problem that you can have in trying to solving the problem with the embedding. And how do you solve this? So the embeddings design pattern actually addresses the problem of representing high cardinality data densely into the lower dimensions, essentially. So what they do is they pass, but you pass the input data into the embedding layer that has trainable weights. And this maps the high dimensional categorical input variable to a real value vector, essentially, in some of the low dimensional spaces. And this will map to the high dimensional categorical input variable, and essentially to the real valued vector in these low dimensional spaces. The ways to create this data representation or dense representation are actually learned as part of the optimization to that problem. So that is one. So in practice, these embeddings actually sort of end up capturing the closeness of the relationships in the input data. So this is just one example, and embeddings is a large, massive topic. So I'm just kind of giving you a bit of a high level, so we tend to get a bit of an understanding of how it looks like. Let me go to the next slide here. So the other sort of design element that is interesting is, let me just sort of see if you have any questions. Awesome. So I guess you guys are still here. Pretty cool and very nice. Okay. Let me just see. Awesome. So cool. Let me go back to the okay. Let's take the other element, just picking up some random elements, design elements. So in multimodal or multimodal sort of design elements, it's a design pattern that addresses the problem of representing different types of data, or data that can be expressed in difficult, complicated ways, complex ways. And how you do is you can concatenate all the available data representation. So what is the problem here? So typically, sort of you have an input to a model that can be represented as a number, or it can be represented as a category, as an image, as a video, as speech, or some other form of free-form text. And many of these off-the-shelf sort of models are defined for a specific type of inputs only. And you can imagine, for example, just keep turning camera on and off just to make sure that you don't get distracted from the slide and myself. So, if you're looking at, a lot of people train with the ResNet 50 data set. So that is specifically meant for certain input sort of values that you can put into. For example, you may not be able to use a ResNet 50 model, essentially, because it does not have the ability to handle inputs other than images, right? If, for example, I'm trying to do, and there is an example here as well, and this is the example. For example, this image that you're seeing here, not sure if I can zoom this. It's basically all the cars, they're parked in a harbor. So I just picked up a video of Tesla cars that are parked. They come over to the Netherlands and they're parked in a harbor before they're picked up and they're taken to their specific distributor locations. Now, this might seem like a static image, but it's a video, it's a video capture. And if you're looking at, which color of cars are where, et cetera, you might probably use a model that takes input of images, for instance. But if you're looking at motion and where sort of cars moving and sort of how they're transported from location A to location B, and how the influx and the outflux of the cars coming from the ships onto the harbor and then moving into a certain location, which allows you to actually start thinking in many, many different terms on safety, security, theft, et cetera, insurance, all those things, then you need a different sort of data set that understands these different modalities. So that's what I mean. So let me just turn off the camera so we can sort of keep focusing on this discussion. Let me also see if I have a pointer, laser pointer. Great, I guess you guys can see my pointer. So for example, here, this is what I meant. So here's the image of the car features where car footage, video footage is in a harbor. Now, what happens is, so for example, you have, I gave you the example of a Tesla car. So you want your model to handle both the image data and also some other metadata from the image captured. So, the other, what I just mentioned was the video data is another metadata, but you could also have some other numerical data. For example, when did the cars come? What time of the day, day of the week, the weather, and all other sort of factors that could be potentially depicted. And you add these, and speech, et cetera, as well, trying to capture more information around the specific And then this becomes sort of multimodal data problem that you need to solve. Now the problem, what occurs when training a structured data model, when you have the inputs in a free-form text, right? So unlike numerical images, text, they can only be fed into a certain model. What happens is you need to represent the image and text inputs in a way that your model can understand. So like I just mentioned, sort of embeddings does solve that problem already for you. You can combine these inputs with other tabular features. For example, you might want to predict sort of, let's say you're going to a rock concert or a music concert, and you want to provide some ratings as to, how much did people pay to a classical music or to action movie that they watched. So for a very simple example, you can take this as sort of or it could also be visiting a restaurant or visiting or taking an Uber car. So you can combine these tabular metadata essentially, and the event you can or about the specific event, eating at a restaurant or driving inside a Uber car, and you can combine the numerical and categorical features. And these are possible sort of, you can have options like meal type or car type example. For example, a car type in an Uber could be a normal car or an XL, or it could be an Ola if you're in India, for example. And these categorical features represent, you can represent these as an array, and you can combine it into some kind of, for instance, the total meal total spent $80 or 2,000 rupees or 50 euros, or the driver total, Uber driver total. You also get those kind of sort of inputs from Uber when you're using Uber. And essentially what you do is you add the price of the meal or price of the drive which you have taken, or any other sort of business domain, think from your perspective. You can add that as a fourth element. And what happens, and obviously this is not a sort of a theoretical lecture, and what will happen is the embedding design pattern it's a common approach to encode the text into machine learning models. So basically you're essentially encoding these, and if your model only had only text, so it would represent, you could represent it as an embedding layer. And in using it, you could use very simple sort of, for example, in PyTorch or TensorFlow, you could just use tf.keras and solve that problem. Multi-label. So as unlike the multimodal or where we have multiple modalities of the data or the problem that you're trying to solve, multi-label is another problem that is actually seems like an inverse of a problem. So basically, the multi-label sort of design pattern, it basically refers to a problem where you're assigning more than one label to a given training example. So in this case, again, I took car example, for example. So, in AI or machine learning, these design patterns actually require changing the activation function used in the final output layer of the model and choosing how the application will parse the model output. So you need to sort of see that there is a difference. It's different from the multi-class classification problems, right? So it's not like, trying to detect whether it's this type of a breast cancer or something else. It's essentially multiple labels, different labels. So now you have different sort of, for example, you may also hear that or see that the multi-label design pattern or design elements is referred to as multi-label, multi-class classification, since it involves choosing more than one label from a group and from more than one possible class. So when you discuss this pattern, you're basically, let's just kind of take a look at just the machine learning or the neural network aspect of it. So the problem is often these model predictions actually task an individual, these tasks involve, they apply a single classification to a given training example. So this prediction sort of from n possible classes where n is greater than 1. And in this case, you have a common sort of, you can use softmax, as the guys who are, most of you, if you're used to using deep learning or machine learning, specifically deep learning, when you have your softmax as an activation layer to actually output the list of probabilities. So once again, I will stay away from not giving you a theory lecture. There's lots of interesting things we do on our live AI. You can follow those theory lectures that goes into details of what it actually means. So what you're basically trying to do is you use the softmax as an output of a particular model and provide an n element array with the list of probabilities in that. And then you sum it all up and add it to one. So that is sort of something which I guess most of you guys are kind of already aware of. And each value actually indicates the probability of the particular training example. So it could be in this case, for example, a very simple example, you take a car, you take the image, and then, if these were 10 different sort of examples of 10 different vehicles, it would give you values of, well, let's say, in a certain softmax output, it would give you, I don't know, 0.1, 0.89, 0.01 kind of values. So then you would say, okay, so it is not an Audi, but it certainly is a BMW, 89% BMW, and another maybe 1% Tesla. So that is the way sort of you can sort of take a look at and try to understand how a multi-label sort of a design element looks like. So but the thing is, in image classification, for example, you could use these training examples to essentially depict what is that. So is it a car? What kind of a dog is it? Or what kind of a cat it is? You could also take this into actually your text examples. For example, in a data set from Stack Overflow, just a nice example. You could take a question and actually you could build a model to predict the tags associated to a specific question. So for example, if we're asking a question on what is the difference between activation functions, or how do I use a specific sigmoid or a logistics activation function, and how do I plot these into a pandas a data frame to get me an answer. So you could essentially, they could be tagged as machine learning, deep learning, Python, pandas, data frame, etc. Now, the solution for building the models, that can assign more than one label to a given training example is to use, for instance, a sigmoid function in your first output layer, rather than generating an array of, where all values, they add up to one. So each individual value is a sigmoid sort of array float, with that is a floating point between 0 and 1. What does it mean is that implementing a multi-label design pattern, your label needs to be multi-hot encoded. So that's a bit of a sort of a solution with which how you can sort of approach this problem. I guess so there are more of these examples. I won't go into the detail given sort of in the interest of time. And sort of each of these examples, they require you to understand and test your data set, understand, for example, the modality if you're using a multimodal, or the classification, multi-classification tasks, or multiple labels, etc. So basically, so this is a bit of an example. There are more. I will be adding a lot of these. I won't go into the details. For example, I'm beginning to sort of we'll create a lot of code as well for you guys eventually. But the whole idea is sort of, there's a few dozen of these examples, ensembles, for instance, and it's here as well. Then you have a bunch of ensembles like bagging, boosting, stacking, and all these examples. I do, however, want to spend the next 10 minutes, 10 to 15 minutes, taking you into a very interesting domain. I know transfer learning, sort of, I also mentioned in the beginning, is a fascinating new domain, which has actually dramatically enhanced the way we have used machine learning or deep learning into all our computer vision tasks and NLP, language learning tasks. So let's take a look at a few of these, which is sort of an interesting sort of model for a lot of folks. So first of all, transfer learning itself has like, I don't know, 24 or maybe 25, easily 25 to 30 different sort of elements to it. So let's just go through a few of these transfer learning elements. I'll just go quickly to the other screen and try to see if you have questions regarding. So there are still no questions. Awesome. I just wanted to check the questions. Abdullah has great coincidence for me for the examples mostly come from embedding designer recommended system. Nice. That's good to hear. I'm glad to hear, Abdullah, that that is how you're experiencing it. I just want to kind of go back here. So the transfer learning obviously is a fascinating topic, right? So, and here I've just added a few examples. There are three examples. We'll just go into these examples and see how far we get there. So let's start with the feature-based. There is this instance-based, feature-based, and very different kind of domain adaptation-based transfer learning models. So let's take a look at the feature-based model. So the common idea around the feature-based sort of transfer learning is to learn a pair of mapping functions. And you need to map these to map the data respectively from the source domain and the target domain to a common feature space where the difference between the domains can be reduced. That's what you're trying to do essentially. So after that, you have a target classifier. You need to be that needs to be trained. And I think you do that already when you're sort of training the models or taking someone else's code. But just for your understanding how this works is important to know. So what happens is you're basically trying to reduce the difference of the domains, but with each sort of problem comes a different problem. For each challenge there is a different problem that is posed, and it needs a different solution. And that's why you have various transfer learning design elements that have erupted in the past decade or so. So basically, for testing on a target domain for the unseen data, you have to first map the data onto the new feature space. That's what you do essentially. And then you perform the trained target data set classifier to make the predictions. So that's what you do. So the detailed motivations and assumptions of learning the pair of feature mappings behind different feature-based approaches are different. And we're just going to take a look at a few of the feature-based sort of approaches and classify these into a few categories. And basically the whole idea is that your approach is to learn transferable feature space across given targets and source domains by minimizing the domain differences. That's and this is what we call a domain discrepancy. So that's and you have to do it explicitly. Another category of approach is to learn the universal features that are expected to be high quality features from across all domains. And there's another category, that approaches is based on feature augmentation. So you can do feature augmentation as well across domains that seek to actually extend the feature space by considering extra correlation learned from the data. So let's go deeper into this specific, the one on the left, feature-based transfer learned model. And let's see if its transition is happening well. Yeah, great. So here, basically, again, I will not go into the details. Transfer learning is a huge topic. People have written hundreds of pages of books on transfer learning, and it's all about how and what are you doing to actually apply transfer learning for what specific problem that you're trying to solve. So you could almost say it's transfer learning is probably one of the mother design elements / design pattern that you need to understand well. This specific example is of maximizing or transfer learning model, which is called MMD. What it stands for is maximum mean discrepancy. So MMD is a non-parametric sort of criteria to measure the distance between the distributions based on the kernel embedding in the reproducing kernel Hilbert space. So it's called RKHS. But again, there's a paper written, and I will share the link of the paper as well. If you're interested in reading the research paper, it's written by Gretton et al. I think it was in 2005. But like I said, we're not going to go into the math, just very high level. In the context of sort of deep learning, researchers have proposed to use neural networks to basically approximate the feature mapping. That's what you're doing. and this is induced by using by a kernel function. So, for example, you could propose to encode the maximum mean discrepancy between the domains, and is to measure the distance between the hidden feature learned in a convolution neural network, for example. That's what this example is about. And in this way, the network automatically learns to cross-domain representation by jointly maximizing the label dependence if available, and maximizing the domain invariance as well. So the base deep sort of architecture looks like this. And you have, in this case specifically, so I'll just sort of speak more in higher terms. So on the left, you have your XS, which is your sort of input space or input data, which belongs to, and when I say belongs to, so it's an element of, mathematical symbol, element of, your source domain, which is XS, capital S. And then, if I have, the next time I'll have my iPad, so I'll also scratch on it to make some a little bit more sense. So it's all you're seeing, basically what I'm trying to say is that you have your input data from the source domain, and then you have your input data from your target domain. And essentially, the input data source domain, so the XS and XT, are transformed by the first several layers in your convolution neural networks. And similarly, you do that also in your text NLP models. The transformation with the first layers is actually considered the approximation within the MMD E. So basically, that's what it is, your maximum mean discrepancy. So that's what it looks like. It's a bit complicated, but don't worry too much about it right now. We will sort of provide full and more detailed explanation. I will do that so it becomes a little bit more, you understand what you're doing and why you're doing it. I have no idea, my phone keeps sending me messages. Anyways, so the other is, so we looked at the feature-based. Now let's take a look at the model-based, which you guys are mostly used to. And I've tried to put in an example that makes more sense. So essentially, the model-based transfer learning sort of model, researchers have been doing this. They've attempted to kind of leverage the powerful expression of your deep learning to extract and transfer knowledge using these relationships of these categories. And the knowledge distillation techniques, which involve, for example, a teacher network and a student network, is a pretty good example. So it's basically knowledge distillation. It's just a distillation technique. It's also called soft labeling. So it's basically a distillation technique called soft labeling. It's proposed to do this model compression. Essentially, that's what you do, in which you can regard the source domain as being identical to the target domain. In the model-based transfer learning, you could distill a soft label for sort of a soft label L, let's say, for a category K, and you average over all this over the soft max of all the activations of the source example of that category K. That's what you do, and you denote this average with sort of L and then K, and essentially you can denote and then in this case you can have a simple sort of softmax that produced a peaked distribution. It can be used, and you can use the softmax as a high temperature T, so that the related classes can preserve enough information about the relationship among the classes. That's what it does. So in this case, basically what is happening is, and I'll just go into the next slide to explain it a little bit more deeper. So you adapt the parameter theta to detect a new class, lions, using this regularizer, so the ohm regularizer. And how it happens is, so in this case, basically this is a regularized based sort of transfer learning model just for you. So if you see the when I use this term, I believe I use the term TLR. Oh, did I use it here? Yeah, the transfer sort of using TTR, that's what I meant. So it's basically a regularizer technique. Let me go back here. minute, I have to be here. So essentially this example of regularizer, so the shared knowledge can also be transferred through regularization. And that's what is interesting to understand. So many researchers have explored ways to use regularization to leverage the transferred knowledge between the source domain and the target domain. And the standard sort of regularization of the model essentially allows you to do that. I won't go into the mathematical notation because it becomes a theory lecture, and we want to avoid that. But I will provide links for you to kind of sort of understand. And I'm sure, I mean, you guys understand regularization to a certain extent. So the target and the source actually model parameters are essentially, they can be modeled essentially as theta s. So what you're doing is basically doing theta s is equal to theta 0 plus vs essentially, and where theta 0 is your task invariant parameter, and that represents the invariant characteristics over the tasks, and actually it's supposed to be the transfer in model-based transfer learning. That's what it is. So essentially, it depicts the feature characteristics of a certain task, and can be learned from data in the specific domain. So that's what is happening here. It's pretty simple. You have a source model from the detected cats and lions. Essentially, you're reusing that parameter theta, and your target model is to detect tiger, for example. And what you're doing is you're using this regularizer, the ohm theta, in order to do that. So essentially, what happens is you can leverage from source models with these task invariant parameters, and they're trained with sufficient data. So that's one of the key things that you need. And the generalization performance for the target model can improve significantly, which you've seen, I guess, all over the world. Let me keep looking back and seeing if you guys are still okay, and if still is interesting learning experience for all of you guys. Great. I believe there is good. There's still some of you guys are here, so that's great. All right. So I think, as I said, there are a ton of things, and going into each design element requires you to understand what the design element needs to do and can do. Understand the limitations, the problems, as we revisit the cardinality issues in terms of, let's say, plural data sets where, you have a child, but a child can be twin, triplet, quadruplet, or gender, where, the dimensions can sort of start increasing as, today you have sort of many of these different ways to look at those features. But now let's kind of revisit and try to understand at a very high level on fine-tuning techniques, which also makes MLOps sort of, design patterns also usable, but also performant. They make, hey. So here is a simple example that I've also taken, and I've provided a link here as well from Yosinki from 2014. So there are many ways. So just a few examples of greedy. I'm sure you're kind of also aware of the greedy layer-wise pre-training and fine-tuning. So the idea of the greedy layer-wise pre-training was widely used to train deep belief networks and autoencoders. And I believe this was happening already in the time frame of 2010, 2011, 12. And I think Yoshua Bengio's paper is also mentioned, has also provided some significant sort of inputs. For example, in this approach specifically for unsupervised learning using initial specific classification tasks. And this approach actually assumes that unsupervised learning tasks, such as an instance reconstruction, can reveal a very good representation. So that's super important to know. The parameters actually initialized with them should be in a good region for the downstream tasks that you're using. So such initialization strategy can be considered as a regularization. So it's also, so this is, I'm still in the TTR design element, and we are trying to look at how to fine tune this. So what happens is you can, it's like a regularization technique for learned model parameters. And a greedy layer-wise algorithms, the first sort of stage is to use unsupervised learning to train each layer. It's known as a pre-training kind of stage. And specifically, then you have the ith layer and essentially the unsupervised model by taking the training examples And then you take these into the output, and these are the output for the next layer to reproduce the representation for the next level. And I'm just avoiding the mathematical notation because it just becomes crazy. You cannot do that in a live session like this. And the second stage is basically, as you can see here, and I will go into the next another slide to explain it more a little bit more briefly. Is fine-tuning the supervised signals from the downstream tasks, for instance, classification, etc. And many variants have been designed for this fine-tuning step. The most common one is actually initialize a linear or a non-linear supervised predictor by taking the hidden layer from the first stage as an input, and then fine-tune the model parameters with respect to the supervised sort of learning loss. So what I'm trying, and then so fine tuning with parameter learned with supervision is also another technique of fine tuning. So while greedy layer is super popular, but it was replaced, as many of it's not as you don't use it often because you have stuff like dropout, and you have your batch normalization to train all layers from in an end-to-end sort of manner, and if you have a more stable optimization sort of methods and large amount of labeled data, you can actually directly train a supervised deep learning model from scratch, and which you're seeing all over the place already in the last couple of years. So the issue, what is the issue here? The problem is actually to transfer the parameters learned from the supervision across different supervised tasks. So, experiments have been sort of conducted in many areas, and transferability of different layers of the pre-trained CNN example, as you can see here again from Yosinki, it illustrates a set of experiments. So, the ImageNet, for example, data set is split into two halves. And then you have, you call it, base A and base B. And the models in the first two rows are trained on A and B, respectively, as you can see here. And then they're used as base models. And the last two rows, the first several layers of this model are actually initialized by learned values, while others are just randomly initialized. And essentially what happens is then, you're just taking the first layers and you're copying from the base model. And then you freeze these into a transfer learning in the next layer. And essentially, you essentially provide an output at the end, and that can be fine-tuned by the subsequent layers. Again, once again, you should read that paper. The whole idea is to try to understand how you can fine-tune a trained learning model, a transfer learned model as well, or a design element. And it is super important, just to kind of conclude this, I guess, this is given in interest of time. And this is, I'll just keep this section open. So basically the whole idea is, let me just quickly go and see if you have any questions. I'm very happy to take any questions if you guys have. Right. So I just have my StreamYard in front of me. So no worries. I believe, great. So if you have any questions, do please go ahead and ask me here or inside the chat. The key, so as you can imagine the design elements, there's no need to create complicated sort of, again, nomenclatures when you're using and understanding of various aspects, be it, ensemble techniques like bagging, boosting, stacking, and various other techniques. Or going into deep learning models, specifically, as you can see, the field of transfer learning is continuously expanding. Multitask learning, active learning, etc., also design elements I will add to this increasing deck, which I'm creating. But the most important aspect is not only knowing what to do with the design elements, understanding and identifying the problem that they pose, and then solving these problems either through fine-tuning methods, if it is transfer learning, for instance, or understanding and providing specific solutions so you can understand the use of this, let's say, your template that you're essentially creating to productionize your MLOps sort of ecosystem, that each design element comes with a set of frameworks, as I sort of mentioned in the beginning, and becomes a template for you to continue to optimize. Because design elements are not meant to provide you sort of robust, boundaries of how you can take a specific solution and deploy it into production. It's a moving target, and in order to understand it, you have to reframe this in continuous MLOps cycles. But the important part is that you have quantified the design element, understood what it can do, and realize what it cannot do. Optimize it or fine tune it, and this is how you can kind of move forward. So I know this is a very high level sort of, I still feel each time I conclude a talk, I think, I think I could have sort of explained a little bit more in detail. But given this is a live session, it's just sort of scratching the surface and talking about sort of, design patterns or MLOps design elements, as I like to call them myself. Is a huge field. You could write books worth hundreds of pages, but the most important thing is to actually understand each design pattern. Take specific code, whether it's a multimodality sort of a data set problem, or sort of a classification or any other sort of issue, and then try to test it, and then eventually try to implement it, and then optimize and fine tune it. So once again, I hope this was useful. It made some sense. I hope because this is work in progress, as you can imagine. There's a ton of stuff that I'm making on a daily basis. And that's just reiterating that this is our way of trying to bring whatever that we are learning on a daily basis, because ML, is an evolving and dramatically evolving space. And ML ops is again an exploding ecosystem, which is creating a lot of sort of bringing some clarity, but also can confuse the ecosystem, given that each vendor is trying to solve their own specific problem, which is great in its own sort of in isolation, but it becomes a challenge when you cannot sort of see how it fits into your end-to-end ecosystem. So this is the whole initiative which I'm trying to do, and hopefully this helps you guys, get some perspective, some ideas. Even if it gave you one or two ideas, I would be super excited to hear from you. Drop me a note. You could ask a question already here, or maybe even after this conversation. And I'm very happy to hear if you have any of these, any questions. So finally, like I said, this is going to be probably, like I said, 2 to 3 dozen MLOps design elements. And each element I will go into detail into explaining, so each element is understood by you. And then hopefully we can also provide code for you to test it and play around with it. And some may be outdated, some are evolving, some are emerging, but the whole idea is to understand it end to end, and that'll give you sort of a collage or collection of your design elements, and then which sort of design element fits to which problem that you're trying to solve with your business. So if there are no questions, yes, there's going to be recording. I think this is recorded already here. But you can search on LinkedIn, but I think I have an ability to also download this video. I use StreamYard, so I believe I can download this video, and we'll try to make it available maybe on our website. So I think it's a good question you asked, Pradeep. We'll do that. Hopefully this is good. It made some sense. Thank you once again. Like I said, we have our own sort of industry vertical projects, which we keep doing, is to keep understanding and applying these things, right? It's not about just theory, because there's a ton of theory lectures online, and it would be ridiculous for me to add another theory. While I do realize that theory your foundational sort of machine learning expertise in theory should be good. If it's great, it's wonderful, but it's good, that's fine as well. But applying these into industry vertical projects like we have in healthcare, energy, HR, manufacturing, our partnerships with all these other big companies around the world is helping us actually expand and create this ecosystem. One last thing, I don't know if you guys know about this. When you see this, it's a European initiative. We're also developing a curriculum, a master's curriculum, together with a few universities. I know we need to make an official announcement, because it's a wonderful, wonderful victory for us. So Live AI is going to be working together with leading industries in Europe to create an AI master's program that'll be worth 60 to 120 ECTS points. So all these things that you're seeing here will be coming into university curriculum as well in some one form or the other. So just keep an eye on it. So if you're a student, if you're looking for, moving beyond your bachelor's to doing a specific master's that involves ethics, fairness, and industry vertical projects like these, keep an eye on Live AI's webpage, but also our LinkedIn page. And some massive announcements will come. We're working with the European Union to actually bring this to, tens of millions of students eventually. That's a wonderful plan. So there are some wonderful big things happening. I just wanted to give you this. I know it's something which I have to officially announce. And we will do that once we have official sort of website that'll come in the next couple of weeks. It'll be alive. So I'll keep an eye on this. And if you have any questions, reach out to me. Anything specific, you can personally reach out to me. I'll answer your questions. I like doing that, and it gives me great pleasure to do that. If not, have a wonderful weekend and stay safe. I know it's still very difficult in India. I know it's heartbreaking. It's really frustrating. So do please stay safe. Take care of each other, and I love you all. See you guys.